Okay, so notes 3.2, polynomial functions and models. So what is a polynomial function? A polynomial function is some sort of function, so like it could just have like an x plus 5, a 2x plus 1, but it's some sort of function where all the coefficients, maybe it has an x squared, maybe it has an x cubed, but all the coefficients, the numbers in front of the x, have to be real numbers. Okay, so obviously no imaginary numbers. They can be radicals, that's fine. And all exponents have to be whole numbers. So the exponents have to be like 0, 1, 2, 3, 4. It can't be -1. It can't be a fraction, anything like that. Okay, so it can't be a radical. So the exponents have to be whole numbers. But the numbers in front of the x just have to be real. Okay, so I show you an example after the next step. And then it says, if this is true, basically, if number 1 is true, number 2 will absolutely be true. So number 2 says the graphs of polynomial functions must be smooth and continuous. When I say smooth and continuous, I mean like it's going to be smooth and continuous. Like a parabola is smooth and continuous. There's no holes. There's no an absolute value function is like a corner. So it's not that, right? Because that's not smooth. It doesn't have like a vertical asymptote because that wouldn't be continuous. Okay, so think about the word smooth and then continuous, it keeps going. All right, so for example, this, so go ahead and jot this down, is not a polynomial function. What's wrong with this? Right here it has a -4th power and exponents have to be positive or to the power of 0, technically. Okay, so some examples of smooth and continuous versus not smooth and not continuous. So this one is smooth and continuous. This kind of looks like a corner, but it's supposed to be smooth, okay? This one is not smooth because right here there's a cusp, and it's not continuous because right here there's a gap, and right here there's a hole. Okay, so not smooth, the cusp, and not continuous, the gap in the hole. So like this jump right here is not okay. Okay, so here's the thing. So it starts getting into really interesting stuff. Ideally, graphs of polynomial functions look like the following. So we know that y equals x looks something like that, right? It's like totally diagonal and it's a line that goes diagonally. Y equals x. We know y equals x squared looks like a u, and it's a really perfect parabola. We know x cubed, y equals x cubed looks something like that. So it looks something like that. Really, it looks like this, and then it goes down this way. But it has this kind of shape to it. And what I'm really trying to do is I'm trying to show you guys that if you have a positive coefficient, the number in front is a +1, what happens is we know that these polynomial functions are going to end up. So see how right here is highlighted? It ends. The end is the right side, okay? The right side goes up. The right side goes up. The right side goes up. All right, what do you think x to the 4th looks like? If you follow this pattern and you start up here, let's see. This one has no turning points. I call them turning points. It doesn't turn. It just goes straight. This has 1 turning point. This has 2 turning point. What about x to the 4th? Should have 3 turning points. X to the 5th should have 1, 2, 3, 4 turning points. Notice that it ends up, and if we draw backwards, 1, 2, 3, 4 turning points, it goes like that. This helps us with end behavior. End behavior is what happens at the very end, and it tells you what happens at the very beginning, basically. So what we know is any odd, so x to the 1st, x to the 3rd, x to the 5th, any odd power is going to have opposite end behavior. See how it ends up, but on the left side, it goes down to the left. This goes down to the left. Any even has end behavior where they're both going the same direction. If it ends up, it also starts above, okay? The middle part, I'm going to tell you now, the middle part is like that varies. It doesn't always look like this, but we know that the end of any function with an x to the fifth with a positive in front is going to look like that. It's going to end going up and it's going to start down here. That's what we know for sure. That's why it's called end behavior. Okay, so if we have all of these ending down, notice how this is negative x squared, negative x cubed. Can you go ahead and draw those? And then it would be best if you highlight these parts where it ends down. I'm going to go in and do that, and you guys are going to do the same, okay? So ending down, see how the end of it goes down and to the right, okay? And it basically looks like a mirror image, right? So any negative x to the fifth will end going down, and then on the left side, it starts above. It starts like up here on the left. Okay, that helps us in a number of ways, and then we'll get back to it at the end when we do the back of the notes as well. Okay, so the first part, I think I do this one for you. Find the end behavior of each function. So for this one, I show you how to do it. So what we really want to look for is we want to look for the biggest power, okay? So the biggest power is going to give us end behavior. So this is a negative x to the fifth. Generally, that's the end behavior. So it has 1, 2, 3, 4 turning points. It ends down, I can tell because it's a negative in front. And if I start here, I draw starting from the end. So it ends down and I go 1, 2, 3, 4, and then it goes like that. So this is generally what negative 3x to the fifth. That's going to tell you the end behavior of this function. I don't know what the middle looks like. I don't know what the y values are. I don't know what the x values are. But I know that the beginning looks like that and the end looks like that. So then we're going to start filling in limits. So these are called limits, but I haven't, we haven't talked about limits yet. I don't remember. So maybe we have actually. But this is the limit on the very left side, this negative infinity, and the very right side, this positive infinity. Let me explain. So for any xy axis, I'm just going to draw randomly right here. So here's your x-axis. So you guys can see, and this is the y-axis, but y is basically f of x, right? So when we go positive infinity on the x-axis, where is that? Well, this is positive. So positive infinity is going to be way on the right side. On the right side of this graph, you can tell the y value is going down, down, down. So that's why the y value is negative infinity. On the left side of the x-axis, x goes to negative infinity. What happens? Oh, the left side goes up, up, up. Up means positive y values. So positive infinity for y. Okay, you're going to try this one. I already highlighted for you, but I wanted you to actually find that on your own. So you look for your biggest degree. And then I want you to write it in. So how many turning points? Which way does it end? Go ahead and sketch the picture and fill it in. Do it for real. Don't just copy me, okay? And then we'll check our answers. So 2 turns ends up. We start here, do our 2 turns. It looks something like that. Okay, so that means on the very right side, what's happening to the y? On the very left side, what's happening to the y values? Did you get that? Hopefully. On the right side, y is going up. On the left side, y is going down. So negative infinity. On the right side, positive infinity. Okay. So another way to ask a similar question. Well, is it? Let me see. Find the polynomial of degree 3. Okay, at the end, it's going to have an x cubed, all right? With zeros at -2, -3, 2, and 5, and then we want to graph the general polynomial. So we're going to graph it on a general graph like this, okay? But we know the -3, the 2, and the 5 are important. So here's how we would go ahead and start it. So I would say, okay, if this is true, then these become these factors. So this is 0. If x equals -3, one of the factors would be x plus 3. And then x minus 2, and then x minus 5. All right, I'm going to put an A up here because it doesn't say that it's like positive or negative. We don't really know, okay? But if A is positive, and I multiply this out, I get a times, so some polynomial is some number times x cubed minus da da da. So you multiply all of that out. You have to do that on your own, okay? And then you go ahead and graph it, and you say if a is positive. So I'll say if a is greater than 0, comma, all of this is true. So what I can do is I can draw myself a little tiny, I'm going to go like this so I block it, a little tiny x-axis, and this is a number line. So I start with -3, and then I have my 2, and then I have my 5. How come there's these little circles and pluses? Because at -3 I have a 0, at 2 I have a 0, at 5 I have a 0. What about to the right of 5? Well, to the right of 5, how do I know that that's going to be positive? You can do a couple things. You pick any number, and if you pick any number bigger than 5, like 10, you plug in a 10, you get a positive. Plug in a 10, you get a positive. Plug in a 10, you get a positive. Positive times a positive times a positive is positive. I do the same thing between 2 and 5. So let's say you plug in a 3. Will 3 work? Yeah. If you plug in a 3, you get a positive. You get a positive, you get a negative. Positive times a negative is negative. So that's how I get the pluses and minuses. How else can you do that, guys? If it's degree 3, if it's x cubed, and it's a positive a value in front, shouldn't it look something like this? Just like this, positive x cubed? So you know that it's going to be positive, and then go through negative. So it starts positive, and then negative, positive, negative. So it looks something like this. So it touches the x-intercept at -3, at 2, and 5. It starts above, that's positive, and then it goes under, and then it goes over, and then it goes under. See how this shape kind of matches that shape still. So the shape is the same, and now we have a general polynomial if a is positive. So we do have to specify if a is positive, this is what it looks like. Okay. So moving on, we're going to come back to this. Don't worry, this is so important, okay? So on the back, it says, okay, power functions. What's a power function? A power function is y equals some number and then x to the some number. So that's basically a power function. So it'd be like y equals x to the 11th, y equals x to the 100th. That's a power function, okay? So it's just like one single monomial. So that's the power function. Okay, so you highlighted some things, and then yours already says odd, so we don't have to worry about that. Okay, so in general, this is what an x squared looks like, and these are the properties. This is what an x cubed, like a perfectly x cubed, 1x cubed looks like, and these are the properties, right? So we should know this already, but I'm just reminding you. Okay, so what happens is, I'm gonna say it first. What happens is, for any even power function, any even monomial, if this is like x to the 10th or x to the 100th, it still kind of looks like this, but what happens is it gets smushed onto the y-axis and smushed onto the x-axis. So that's what I try to say here, but I'm just going to say it out loud as if this is x to the 7th or x to the 17th, any odd power, then it's basically going to look the same, but it's going to get more smushed onto the y-axis and smushed onto the x-axis. So I give you an example right here. So here's your original solid x squared. What does x to the 8th look like? If you put it into your calculator, it's going to look kind of like this. It gets more, see how it squishes onto the x-axis, and it also gets squished onto the y-axis. It's like you're taking it and you're squaring it. So you're like pushing it in on the left and right, and you're pushing it down onto the x-axis too. So you just take this and you push it in, and then you push it in the middle. Okay, so that's what x to the 7th would look like compared to x cubed. So what I want you to realize is it basically looks the same, but it gets like a little bit more smushed. That's it. Okay. Okay. And then we're going to go on to multiplicity. Oh my God, I love multiplicity. Seriously, it's the best, and it helps so much in calculus. So it has a lot of words. You can read all the words, but basically this is what you do. Multiplicity is referring to the power. Okay, so once you have everything factored, multiplicity is the power. That's why I put m there. If m is even, the graph basically just touches it. It touches like the x-intercept, and then it bounces off. But if m is odd, then it crosses the graph. So let me remind you what this looks like. So these have all odd multiplicity, because what is the multiplicity? The power is 1, 1, and 1. Those are all odd. So that's why all of these cross the x-axis into the bottom. They cross it up there, and then they cross down. Okay, when I'm talking about an even, let's say you have x minus 1 squared. What does that look like? Well, it looks like a perfect parabola, but shifted to the right. So it goes like this. Here's 1. And it looks something like that. See how when it's a even power, it touches and then it bounces back up. So that's what I mean by touches or bounces, okay? So here's an example right here. So I did it for you right here. And then it says, okay, so let's say you're gonna graph an easy version, a general version of this. Well, first you have to realize this is a power of 1, a power of 2, a power of 4. If you multiply those together, which you technically don't even have to multiply all of it together, you're just doing x to the first, x squared, x to the fourth, you get x to the 7th. So then what you're doing is x to the 7th has a certain end behavior. X to the 7th with a positive 5 in front means you start up, and then how many turning points? 1, 2, 3, 4, 5, 6 turning points. So it's always minus 1 for turning points. That means you start up here on the right, and then it ends down here on the left. So what you know is that on the right side of your graph, it starts like that. You know that for sure. And on the left side, it's going to end down here. Okay? So here's the rest of it. You're going to list it really neatly, just like I do. X equals 2. So if this is the factor, if these are the factors, that means x equals 2 is a solution. And then the multiplicity is 1. So I write m is 1. And I do a little x. If you want, instead of crosses, you can put a little x, or you can put a c for crosses. It's up to you. But you have to tell me like the multiplicity at 2 and then what happens because of that multiplicity. Okay? And then at -3, x equals -3, the multiplicity is 2. 2 is even, so it touches. So I just put a point for touches. Like crosses is an x, and then I do a point for touches. If you want to write t for touches or b for bounce, that's fine as well. Okay? And then x equals 4. The multiplicity is 4, which is even, and then it touches also. So even touches. So I just write a little point. So here's how I draw it. I start up here because I know the end behavior starts up and to the right. And then I go to 4, and 4 touches. So that means I bounce back up. And then I go to 2, and 2 crosses. So I cross it down here. And then I go to -3, and -3 touches. So then I bounce back down. So touches means that it bounces back, right? So it bounces at 4, it bounces at -3. See how this matches this in the end with the end behavior. I don't know what my y values are, but I do know what my x values are. There you go. Okay? Okay, let's try another. So this one you're going to do. So you give it a try, and I give you a little hint here. This is x squared times x minus 2. This will turn into an x cubed, and x cubed looks something like that. I already know my end behavior. You try it. Don't copy me. So list, right here, list your your zeros, list your multiplicities. Tell me if it's crossing or touching, crossing or bouncing, and then go ahead and draw it and see what you get. Do not copy me, and then I'll show you slowly. So I got these two, right? So at 0, x equals 0 and x equals 2, At 0, the multiplicity is even, which is 2, so that's even, it bounces. At 2, the multiplicity is 1, and it crosses. Okay, so I start drawing it, and then I start on the right side, and it should look something like that. So on the right side, it's up here. See how it's up here? And then at 2, it says cross. So I cross down. And then at 0, bounce. So I bounce back down. So this shape looks like that shape. So I'm good. I want to compare my shape at the end to the shape in the beginning. Notice that this has the same number of turning points as this. This has a different number of turning points. So this is the most turning points possible, but it can have less. Okay, so this actually, technically, this only has 1, 2, 3, 4 turning points instead of 6. But that's okay. This is the most that it can have, and it tells us our end behavior. Okay, let's do one more. So you're going to try this. So do it for real. Do it just like this. So write this first, and then your multiplicity, and then make your drawing. Okay, so let's see. Oh, sorry, this has a lot more information. Okay, what degree is this? Okay, well, that helps if you did that part, right? So degree, second degree, third degree, second degree, it's going to be degree 7. It's going to be a negative x to the 7th. It's degree 7. Intercepts. Well, intercepts, what do you do to find the y-intercept? What do you do to find the x-intercept? List them both, please, please. Okay, list them both. Well, the y-intercept is 0, 0, and there are 3 x-intercepts. I know that these are the same, but please list them for each one. So those are your x and y intercepts. And then multiplicity. Okay, you can go ahead and list your multiplicity just like over here. You're listing your multiplicity. So there's 3, there's 0, 2, and negative 5. You list your multiplicity and then tell what they're going to do. So bounce, cross, bounce, right? All right, the power function resembles what? So the power function is going to be like, what does it look like? So generally this is a negative x to the 7th, but the power function resembles negative x to the 3rd, right? So it either looks like x squared, an x squared or negative x squared, and then an x cubed or negative x squared. That's what it means by resembles, okay? The power function itself is negative 4x to the 7th. But there you go, okay? Turning points. At most, because this is 7th degree, at most 6, and it ends down. So I drew what it should look like. So it has the same, so here's why this is important. This, when I draw it with a 7 degree and it has a negative number in front, it ends down, and then I have 1, 2, 3, 4, 5, 6 turning points. But this end behavior, if I cross out the middle, look how it matches this. So that's why the power function, that's why that's important, because then I can just right away go, okay, is this really like an x squared or like an x cubed? And then I can draw that and be like, okay, this is what it looks like in the beginning and at the end. And I say 6 at most is because remember how over here we said this could have 6, but instead of 6, it only has 4. So it can have any like even number down, right? If it's not even, then it's not going to have that same end behavior. Okay. And then what is the end behavior? Well, I can just look at this and I can tell. So on the very right, the y value goes down. On the very left, the y value goes up. Okay. And then you're going to graph it. So go ahead and graph it just like we did the other ones. And then you're going to check your graph. Don't just copy me. And it should look something like that. So your graph ends down at 2. See how it crosses? So it goes up. At 0, it bounces, goes back up. And at negative 5, it bounces, goes back up. And notice how these end behaviors are the same as these end behaviors right here. It's the same as these end behaviors right here. This power function looking like negative x cubed has 2 turning points. This one says at most it has 6. How many does it really have? 1, 2, 3, 4. It has 4. Do we know that until we graph it? No, we do not know that until we graph it. Okay, but generally this is what it looks like, and then you can tell you're right because it matches your work over here. It matches the end behavior over here. So everything will match up in the end. All right, so there is 3.2. I love 3.2. This is going to be on your quiz on Friday. You can do it. Okay, bye.